But what can we do with recursion? So we can make cool designs. That's fun. We can do countdown things. We can do some tricks. But is there anything actually valuable that we can do with recursion? And the answer is yes. Recursion is really good if you set it up correctly. Recursion is really good at exploring data structures when you don't know the size or the shape or what's here. Now, if somebody says, I have a nested list like this that contains names, and I can tell you that that list has 3 levels to it. If you told me that much information, I could use nested loops to discover the names of this nested list. I could do that. But if you don't tell me how many levels deep it goes, I don't know how many nested loops to do. But using recursion, I can actually create code that will process this list, and I could create a very accurate description of what's in this list, how many things are there, what the item names are. I could really comprehend this list very closely using a relatively small amount of recursive code. Because what happens is it will just keep digging until it reaches the bottom level, and then it backs its way out, just like we said. So let's take a look at how that would work. Let's break the list up like this, okay? So you can see this list, if I break it into levels, looks like this, where Adam is this A list is the main list, and it contains 5 items. The first item is a string. The second item is a list, right? In the second level list, it's got 4 items. I've got the string Bob, and then I've got a list, Chet and Cat, and then I've got Barb and Bert. Okay, this one has 2 items in it. So, as I understand this list, this kind of structure is also known as a tree structure in computer science. So this is what we would refer to as tree traversal. It's another way of saying comprehending a complex nested data structure. And so if I take that and I put these lists, you can recognize that they're the same lists with the same structure. And if I take that and I want to know how a recursive program would understand that list, this is how it would work, okay? So it would start with Adam. And the rule that I give it is, if it's a name, then count it. We're counting how many names are in there. So if it's a name, if it's a string, count it. If it's a list, then process that list. So we have a name, we count it. We have a list, we process that list. So we have a name, we count it. We come to another list, we process the list. Count it, then we go back. Once we run out of list, we're going back. Every time you see an arrow pointing up, that's where the recursion is going up a level. So we count it, we go up, back to this list, count it, go back up to this list, count it, we come to another list. But what you can see here is, if I follow that pattern, it doesn't matter how many lists I have, it doesn't matter how many things are in each list, it doesn't matter how many levels I have. This algorithm will work on any tree structure that you can think of. It doesn't matter. And I don't have to change the code at all. So it's a very powerful concept because the code is actually flexible to the point where what it's processing doesn't even matter. And so the logic there is, for each item in the list, if it's a single item, a string, we're going to count it. Otherwise, process it like a list, which means recursion. We're calling that function. So